Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in Applied Electronics, and we have been going through the paper on physics of materials, and we have been seeing in the previous lectures the primary bondings and secondary bondings which exist in solids, and in general we have been seeing number of lectures on bondings in solids, and in this lecture, that is lecture number 10, we will see mixed bonding and the comparison between different bondings, which we have seen so far to a greater extent. Now, what is mixed bonding? Now, we have seen the primary bondings in namely ionic bonding in NaCl, covalent bonding in silicon, and metallic bonding in pure metals like aluminum and so on. What is mixed bonding? Now, if these bondings are mixed, maybe if you look at some of the 3-5 compound semiconductors where you got more than one species, then you come across what is called mixed bonding. And it was Linus Pauling, the double Nobel laureate, he gave a formula using which you can calculate the percentage of some kind of bonding that you normally do not expect. We have been taught in the primary classes that in all covalently bonded solids, in all semiconducting systems, the bonding is covalent, but it is not true. And then the contents also will have comparison between different bonds. So, mixed bonding, as I told you, the credit goes to Linus Pauling, who gave an expression for ionic cum covalent mixed bonding. As I mentioned to you just now, you take a 3-5 compound semiconductor like gallium arsenide, or even you can take a solid like MgO. MgO is a ionic system, but what is the percentage of ionic character? It depends upon X A and X B or chi A and chi B, where chi A and chi B are the electronegativities of the two elements which constitute the solid. Now, therefore, you take the example as I told you, the magnesium oxide, the percentage of ionic character is given by an expression of this kind, where you have got 1 minus e to the power of minus chi A minus chi B to the power of 2 by 4 into 100%. That gives the percentage of ionic character, where chi A and chi B are the Pauling electronegativities. The electronegativities are given in the Pauling scale. there are other scales as well. So, the value of chi mg is 1.3, whereas for oxygen it is 3.5. You now substitute these values in the expression given here, that makes you to obtain the percentage ionic character for magnesium oxide as only 70%, but in general you say NaCl is ionic compound, where the ionicity will be not 100%, it may be around 96% or so. Similarly, you call MgO as an ionic solid, but the percentage ionicity is not 100%. That is the important point. That is, this becomes much more important when you go to some of the solids semiconducting compounds, right. Now, I will come to that later. Now, let us now pass on to the again the electronegativity scale according to Pauling, right. The Pauling's electronegativity values are following. Now, it varies from 0.7 to 4.0. Now, what is 0.7? It is the electropositive element like cesium that you have here, francium, cesium, they have got 0.7 in the Pauling scale. That means, how do you define electronegativity? It is the ability of an atom to hold the electron to itself, and it has a least value of 0.7 as against 4.0 possessed by fluorine, right. You observe here fluorine which has got 4.0, that means it is a super halogen. It has got the ability to the highest ability to hold the electron to itself. Supposing it gets an electron, suppose an electron goes nearer to fluorine, fluorine will capture the electron, fluorine will never allow the electron to get out, right. The holding capacity for fluorine is maximum. So, it is the most highly electronegative element in the whole of periodic table. The electronegative element, whereas they are called electropositive elements, right. They have got a tendency to release the electron. You take NaCl, sodium has got a tendency to release the electron, whereas chlorine has got a 3.0, that means a tendency to accept the electron, right. So, that you should understand that sodium has got the tendency to give the electron, whereas chlorine will accept the electron. Therefore, chlorine is electronegative, whereas sodium is electropositive. Okay, these are the values given here. The value ranges from 0.7 for cesium and 4.0 for fluorine. These are the two extreme ends for the electronegativity values. Now, we can think of mixed bonding, metallic covalent mixed bonding. The transition metals are an example where the d electrons, s electron, the dsp bonding orbitals lead to high melting points. Then ionic cum covalent mixed bonding, many oxides and nitrides are examples of this kind of bonding. Now, let us put the values corresponding to Na and Cl. As I told you just now, the ionic character will be 0.94, it is not 100% ionic, right. The more important thing is you should note that silicon, the fraction ionic character is only 0.0. That means what? It is fully covalent. You should understand silicon is a monatomic species, right. You have got only one kind of atom, silicon, 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 so on. So, if you consider similarly germanium crystal, they are examples wherein the bonding is fully covalent. On the other hand, you go to gallium arsenide, right. In a periodic table, if you go to gallium arsenide, it is a 3,5 compound semiconductor. The third group of gallium is combined with arsenic, which belongs to the fifth group, the 3,5 compound semiconductors. Then maybe you can think of indium telluride, it is a 2,6 compound, right. Zinc sulphide, it is again a 2,6 compound. Why it is called 2,6? Zinc is the second group, sulphur is the sixth group. The 2,6 compound semiconductor, you observe here when the the ionic character becomes 62%, right. Zinc sulphide or indium telluride, indium phosphide, they are called as semiconductors, right, but still in semiconducting systems the bonding is highly the ionic characters substantial, right. It is the degree of ionicity is substantial even in semiconductor system. That is a very important thing. You take gallium arsenide, the LED light emitting diode. Now, this has got 31% ionic character. In some other cases, it is around 60%. Now, therefore, the fractional ionic character is important, and again the point to be understood is the compound semiconductors like gallium arsenide, indium phosphide, indium telluride. If one asks a question, what is the bonding in semiconductors? Now, you should not say it is covalent bonding, it is wrong. Only in silicon and germanium the bonding is fully covalent. In other cases, it is partly covalent and partly ionic. The ionicity, percentage of ionicity depends upon, as I told you, the electronegativity values, right. It depends upon chi A and chi B, right, the electronegativity values. Now, therefore, you have a graph now wherein the percentage of ionic character, the amount of ionic character given along the y axis as a function of electronegativity difference. As I told you, if the electronegativity difference is large, the percentage ionic character will be large, right. So, lithium fluoride has got the value like around 1, or percentage means it is around 0.9, means it will be 90%, right. Whereas, you have here around 0.5 or around 6 lithium iodide. So, 60% will be the percentage of ionic character, right. So, the percentage of ionic character is given in terms of the electronegativity difference, right, because the Pauling formula dictates the amount of ionic character in terms of the percentage of electronegativity. Let me now summarize the covalent bonding, the properties or the characteristic features of covalently bonded solids. It is usually formed from 2 electrons. You know the case of hydrogen molecule. What is hydrogen molecule? Now, the 2 electrons associated with 2 hydrogen atoms, they are shared between the 2 atoms, right, the 2 hydrogen atoms, giving rise to what is called the covalent bond. So, usually formed between 2 electrons, one from each atom participating in the bond, and covalent bond is strong bonding, the primary bond. Again, the bonding between 2 carbon atoms leads to diamond. It has got a strength, a very high strength. Diamond has got a very high strength. That is the reason why you make use of diamond for a cutting, diamond as a cutter, or hardness testing machines, you make use of diamond as for testing, right, the hardness testing. I want to test the hardness of a aluminum or some material, I am using maybe tungsten or diamond indenter or a tungsten indenter, right. So, these materials are having high melting point and therefore, high hardness. So, it has got a high strength or high hardness, right. Now, compared to sodium chloride, now the bonding that exists between carbon atoms is very high, or in other words I will say that diamond has got a highest hardness. Covalent bond is strongly directional, and it gives typically to low filling space. The packing density in silicon or germanium, have got low APF. APF means atomic packing fraction, as against the face centered cubic structure and body centered cubic structure. Now, we will be seeing about these structures, the crystal structures, in the lectures to come in the next chapter, but I would like to mention at this point of time diamond or silicon, germanium, they belong to loosely packed structures, the packing density is low. Okay. So, the packing density or the amount of filling in a given volume is low in the covalent bonded systems, right. Now, this is a FCC structure of diamond. You see lot of volume is remaining unfilled, right. This is the structure of diamond. People wear the diamond ring or diamond ear stud, where what is diamond is nothing but carbon atoms, right. But and it has got a structure like this, that is the atomic arrangement will be looking like this, right. Each atom is a carbon atom, right. This is atomic structure, this is the FCC structure of diamond, and but even though it is FCC structure, it is two interpenetrating FCC lattices, and the packing density, as you will be seeing in the lectures to come, is only 34%, right. Out of the total volume of the unit cell or A cube, the volume of the unit cell, only 34% is filled by the atoms, the remaining percent is remaining vacant, and so it is a loosely packed structure. Again, covalent bonded solids like diamond, it should be an insulator, okay, because it has does not have free electrons. And in a covalently bonded solid, the electrons are said to be shared. Sharing is not a proper term, but still they are bound to each other, right. In a hydrogen molecule, the two electrons are bound. In silicon also, the electronic configuration and things like that, the S2 P2 configuration, the electrons are shared. Because the electrons are shared or coupled to each other, you do not have free electrons. When you pass a current, when you apply a voltage across a semiconducting material, you do not have electrons to go in a particular direction. If electron goes in this direction, the conventional current is said to flow in the opposite direction. So, that kind of currents will be absent in the case of semiconducting materials. So, in covalently bonded solids, the electrons forming the bond tend to be localized in the region between the two atoms joining the two atoms. So, there will be no current. Okay. Then another point is the spins of the two electrons, as I told you in the previous lecture, which are participating in the formation of covalent bond, will be antiparallel. You know very well that in hydrogen molecule there are two electrons, and one electron will have spin up, the other will be having spin down, or the two electrons, one will have up spin, the other will be down spin. The two electrons which are participating, which are said to be shared, they will have anti-parallel spin orientation, right. That is important. Then the Pauli principle modifies the distribution of electronic charge according to the spin orientation. What I would like to tell you is the electron density is directional, it is not uniform, right. So, the bond is a strong bond directed low space filling. I mean, the bonding is anisotropic and the space filling will be smaller. The structures in which your semiconductors are formed will have the space filling will be smaller. Okay. That is what I showed you just now. So, the material will be hard like diamond, but brittle, and but the melting point will be again high. You pass on to the van der Waals interaction in crystals of inert gases. Inert gases like helium, neon, argon, krypton, xenon, radon, they belong to the inert gases, right. Why are they called inert? They obey the octet rule, having a configuration S2 P6, that means the fully filled shells. So, the valence will be 0. So, there will be no electrons which will participate in a reaction. So, the gases do not react, right. That is the reason why they are called inert. So, here you have got induced dipole-dipole interaction, which can be described by Lennard-Jones potential, as I told you in the previous lectures. The outermost shells of atoms are completely filled, okay, with spherically symmetric electronic charge distribution, and the electron distribution in crystals is very close to that of free atoms, because you do not have electrons in between, right, because the closed shells are there. Bonds are very weak and crystals are transparent to insulators. The bonds are, the van der Waals bonding comes under the secondary bonding. So, the bond strength will vary from 1 to 20 milli electron volt. The spin dependent Coulombic energy, exchange interaction will play a role. The isotropic interaction in the crystal, the atoms packed together as closely as possible, right. The crystal structure will be mostly closely packed. So, close packing means where? Where do you find close packing? There should be either FCC or HCP, right. FCC is one of the closest packings. FCC refers to face centered cubic structure, that of course, you would be knowing, or in the lectures to come you will be learning more about FCC, right, how the atoms are distributed in space, right. So, we will pass on to metallic bond. Where do you find metallic bond? You should know that in all metals the bonding will be metallic, maybe iron, silver, copper, gold, the bonding will be metallic. Now, what do you know about metals? They are very good conductors of both electricity and heat. Why are they conducting electricity easily? When you apply a potential, they are able to current flows, right. You say what is current? Flow of electrons. Where from you are getting electrons? It is because of the fact that you see the ions, you have got atoms, right. Supposing you got you know here you array of 4 ions are here, right. Let us assume the sodium ions, right. What is the valency of sodium? It is a monovalent atom, right. You have got lithium, sodium, potassium, rubidium, calcium, rubidium, cesium, right. The monovalent. Monovalence is 1. So, each sodium atom will give 1 electron to what is called the conduction C. What I mean by this is the outermost electron will become a free electron, right, because the valency is 1. What is valency? The very profound words which are used with regard to metals, or how do you define a metal? Metal is one in which you know the valence electrons of atoms become the conduction electrons, right. Valence electrons become the free electrons, or the electrons take part in conduction. So, the valence electrons become the conduction electrons. Now, therefore, each atom will give an electron to the solid, right. The atom, from this atom you will have 1 electron here. So, you find lot of free electrons, right. When you apply a potential across this metal plate, suppose it is a metal plate, right, maybe a copper plate, or whatever you got a metal plate. Now, they are the copper atoms, originally they are atoms, but when the electrons are coming out, the valence electrons are coming out, what remains will be ions, right. How do you visualize a metal? It is made up of ions and free electrons, right. Where from you are getting free electrons? The valence electrons of atoms are given to the material, right. The valence electrons of the parent atoms become the free electrons. You find the free electrons here. The outermost electrons of atoms become the free electrons, and so a metal should be visualized as though it is made up of ions and free electrons, right. These free electrons will take part in electrical and thermal conductivity. I need not tell you about Weidmann-Franz law. A very good electrical conductor should also be a very good thermal conductor. Therefore, in the metallic bond, some fraction of electrons will be delocalized, that means they are made free, and they will take part in the conduction, because they are mobile, right. They are movable conduction electrons, leading to high electrical conductivity. And the electronic structure changes strongly by the formation of a solid crystal. The electronic structure, that how the electrons are distributed, it depends upon the other ions and electrons. So, this is how one you visualize the solid, a metallic solid. Then the properties are, they are moderately strong and isotropic bond. Right? Isotropic means the bonding is not directional. In the case of covalent crystals, semiconductors, the bonding is highly directional, but on the other hand in metals non-directional. The melting point is relatively low, they are ductile, metals are ductile, they can be bent, right. Take a copper wire, the copper wire can be bent, whereas The covalent crystals, because of directional bonding, they will be brittle. So, ductile brittle transition. Okay. You talk of the materials which are glass is brittle, right, whereas metals are ductile. Okay. Ductile materials, strong distortion of the valence electron configuration by transition to a solid does not allow to obtain coercive energy within a simple model. Using a simple model, you cannot explain the coercive energy or the binding energy in a metallic solids, because the many electron system where you got a collection of ions, electrons, you have to take into account all the interactions, right. So, requires computation energy levels of valence electrons in the presence of what is called a periodic potential of the ionic cores. These things you will see at a later stage. Then we will pass on to ionic bonding. In ionic bonding, you know very well NaCl, right. You have got a positive ion and a negative ion, sodium is a positive ion, chlorine is a negative ion. So, you got Q is the charge associated with the two ions. So, the force will be Q square by R square, the square law. The potential will be Q square by R, that is what I give here. The potential will be plus or minus Q square by R, that is the potential that is operating between the two ions. The repulsive interaction will be there coming from the Pauli principle, as you know. Then the van der Waals part of the attractive interaction in ionic crystals makes only a very small contribution. Now, you should remember a van der Waals interaction will be present in all solids, but the degree of the magnitude of van der Waals bonding will be very small. It is because it is a secondary bond, it is often ignored, right. It will be there. Let me now summarize the different bonding mechanisms, the properties and the characteristic features of different bondings, and we have seen so far the primary bondings like ionic bonding, covalent bonding, metallic bonding, and finally, the secondary bonding like the van der Waals bonding. Hydrogen bond also forms a part of the secondary bonding. The hydrogen bond is the one in which one of the species will be hydrogen. You know H2O, H2O is an example for the water molecule, right. Hydrogen bonding will be there, because one of the atoms will be hydrogen, right, and HNO3. So, anyway you got one atom which is forming part of the molecule will be hydrogen atom, that is called a again a secondary bond, so called hydrogen bond. It is a very important bonding, even though it is a weak bond, because in DNA, in biological systems like DNA, the secondary bonding, the hydrogen bond plays a very important role. Of the primary bondings, the binding energy or the coercive energy will be very large. What is meant by coercive energy? It is the energy required to break the bond, right. It is the binding energy will be very large. The binding energy is very large means the melting point will be very large. All of you know that by now. I showed you the binding energy curves. In the very first lecture, we talked about the coercive energy or the binding energy. The binding energy is correlated with the melting point. So, with regard to the summary, with regard to especially the semiconducting compounds, in the elemental semiconductors like silicon and germanium, the bonding is purely covalent. That should be underlined, because we are now I am talking to the electronic students who should be very well be aware of the fact that silicon and germanium, the bonding is fully covalent. And another important point is the space filling is only 34%, right. The silicon and germanium are loosely bonded as against the face centered copper, silver, gold. Copper, silver, gold, they come under face centered cubic structures. The bonding, the space filling will be very large. whereas in the case of silicon the space filling will be small. Then among the semiconductors, from elemental semiconductor you go to a compound semiconductor like gallium arsenide. It may be a binary gallium arsenide or cadmium sulfide or indium phosphide. They are the binary semiconductors. The bonding is not fully covalent, it is covalent cum ionic. Okay. Then the other points are there is considerable amount of ionic character, as I told you, in the case of compound semiconductors, which can be obtained from Pauling's formula, and the above formula depends upon the percentage of ionic character, and I told you the packing density in silicon germanium will be small. Then having said so much about primary bond, the secondary bond, namely the Van Roll's bond, is a weaker bond. We will pass on to the question session. We have the question number 1, what is meant by mixed bonding? Question number 2, how will you calculate the fractional ionic character in gallium arsenide? Of the different bondings, which one is directional? The fourth question will be, which one is the weakest bonding? The final question is whether all the bondings can be present in a particular system. With this, we come to the end of the 10th lecture on bondings in solids. The rest we will see in the lectures to come. Thank you.